In biological systems, alcohol oxidation occurs in quite a different fashion than it does in lab. The reason for that is that in biology the body can simply not use strong oxidizing agents such as chromium or manganese-based agents, since they're too strong and they will oxidize not only the alcohol that the body desires to have oxidized, but also many other things, thus leading to very harmful effects. And so even though the mechanism and the oxidation of alcohol happens in the body as well, the nature uses a completely different oxidizing agent. The oxidizing agent that is used in nature is this formally based pyridinium salt, which has a positive charge here, or nitrogen. This is attached to a sugar residue, and there is an amide functionality here. And this unit is known as NAD+, which stands for nicotine amide adenine dinucleotide. And under the influence of enzyme which is known as ADH, or alcohol dehydrogenase, this dinucleotide adds a hydrogen from an alcohol formally adding it as a hydride anion, and releases a proton, while at the same time oxidizing an alcohol to an aldehyde. This process keeps, and this form of dinucleotide is called NADH, the reduced form, and the product of oxidation of alcohol is acetaldehyde. This then occurs once again to give us acetic acid, and acetic acid is not very toxic and it's soluble in water, and then it's excreted out of the body. Okay? Now, this enzyme alcohol dehydrogenase is designed for ethanol, and the reason for this is that ethanol is a naturally occurring compound. When you have fruits basically rotting on the ground, it will start to ferment and produce ethanol. And since animals tend to eat these things, they needed to have a mechanism which would eliminate this ethanol from their body relatively quickly. And that's why this enzyme alcohol dehydrogenase was developed naturally to correct for these potential problems with their food. And so the ethanol is the best substrate for this enzyme, but the enzyme will work on isopropanol, or ethylene glycol, or methanol. And the mechanism of its action will be pretty much the same, and so it will oxidize methanol eventually to formic acid, and it will oxidize this eventually to oxalic acid. The problem with the oxidation of ethylene glycol and methanol is that formic and oxalic acids are quite toxic. And so even though methanol and ethylene glycol themselves are not overly toxic, these metabolism products of them are quite toxic, and they lead to poisoning. This is particularly problematic with methanol poisoning because methanol is often found with ethanol in spirits of poor quality. The mechanism which is used for treatment of this methanol poisoning is quite peculiar, because since ethanol is the preferred substrate for the enzyme works much better with ethanol. And so in the presence of both methanol and ethanol, the enzyme will preferentially work on ethanol, while in the presence of only methanol, the enzyme will work on methanol, of course. It's the only choice. And so the methanol poisoning is typically treated in hospitals by giving patients, injecting patients with an almost lethal dose of ethanol, which will then keep enzyme busy until all the methanol is excreted from the body in its unchanged form, so as methanol, thus preventing the formation of formaldehyde and formic acid, which are very toxic.